All right, Year 13, we're going to be looking at revising over pipelining. Now, pipelining was something on the mock exam which came up twice, and there's quite a few of you have forgotten the detail of it, so this is why I am doing the video on it. So just kind of recap of the detail. One thing to bear in mind, there's some really big misconceptions with pipelining, which is where most of you fell down, which is why I want to kind of really iron out those misconceptions, so hopefully you won't make them again in the real life one. So let's move on. So when we talk about pipelining, we have pipelining as a concept, okay, because pipelining is a technique that's used all over computer science. So for example, instruction pipelining, where we'll have maybe on the command line we'll have one instruction, then we have the next one, then the next one, and they kind of feed into each other. So the output of one instruction becomes the input to the next. And obviously we have CPU pipelining. One thing to remember is that you need to know about both, okay? The pipeline as a concept, what it is, and also its practical implications for CPU pipelining. Now, where the misconceptions come into this is most of you see CPU pipelining, you remember, well, actually, we're doing the fetch at the same time as we decode and execute something, so it must be running in parallel. But that's not what pipelining is. Okay, so pipelining is where the output of one is the input to the other one. It just so happens that I can do fetch on one instruction while I'm decoding another one. So that's where the parallelism comes into it. But in its strictest form, pipelining isn't technically parallel. Okay, so it's a tiny misconception. It's very subtle, but it's super important because a lot of you can't just make the assumption it's in parallel, therefore everything is parallel when I talk about pipelining. Anyway, let's kind of delve into that in a bit more detail. You'll see what I mean. So, when we're talking about the FD cycle, we are talking about fetch, decode, and execute. Let's kind of just delve into this one. Okay, so any talk about the FD cycle would be remiss without actually reminding you of the registers, because otherwise things always make sense. So there's three registers involved in the fetch stage of the FD cycle. So we've got the program counter, which points to the next instruction to be fetched. Then we've got the MAR, which is going to store the address of the instruction or data that we're going to fetch. Remember, when we're fetching, we may be fetching an instruction in, or it might be data that is required by that instruction. So for example, this is maybe a direct addressing mode, then we would have to do an additional fetch in order to get that second bit of data into it, and that data would obviously have its address stored in the MAR. The MDR will then store the result of the fetch, which will either again be data or instruction. So a tiny bit more detail then. So MAR will store the address of the current instruction to be fetched, or the address of the data the current instruction is going to be acting upon. The result of the fetch is then placed in the MDR, and that will be for both data instructions. And then the MAR will be updated if the instruction in CIR requires more data to be fetched. So if I'm execute or decode and executing instruction which requires maybe using direct addressing mode, then that's when the MAR will be updated with that address to the data that it needs. So after a fetch happens and the data is sent down the data bus, it will be placed into the MDR. So it's going to store the data or instruction, depending what I'm fetching, into the MDR. If it's instruction and it's part of the FD cycle, then that instruction will be copied to the CIR as the next part of that. If it's data, then the CIR will use the data from the MDR in order to kind of do the calculation. We do spend a lot of time looking at the MAR and MDR because when we're talking about FD cycle, those are the ones we tend to update the most. However, the CI is also important, the current instruction register. So when I am executing an instruction or decoding instruction, it will be in the CIR. Then obviously, if it's a instruction which requires more data, i.e. direct addressing, something like that, then the MAR will be updated with the address, which will be the operand of the instruction. And if it's a jump command, then the program counter will be updated because it's got to go to a different part of the program. And again, the operand of the CIR will be copied into the program counter. So Remember that instructions are made up of opcode and operand. Okay, the opcode is what type instruction is this? It's add, subtract, jump, branch, whatever. And the operand is the data it's going to act upon. Okay, and that's going to be either a value, immediate addressing mode, or it's going to be an address, or like a direct addressing. And then if it is an address, that's when we might have to do an additional fetch to get that data in. So now let's go into the nuts and bolts of CPU pipeline. And remember, CPU pipeline is just one example of pipelining. It is the one that's most common when we're talking about A-level specifically. It's the one that you come across the most, but it's just one example. Now remember that pipelining is the output of one stage becomes the input to the next. That is essentially what we mean by pipelining. Okay, so for example, if I'm trying to do my fetch, decode, execute, okay, I cannot do that in parallel. Okay, I just can't, because how can I fetch instruction and at the same time execute it? You know, that's like trying to, I know, write in a book without opening it. Okay, there's a very specific order when I want to write in my book. I have to open it up first, get my pen, then write. Okay, I can't open the book up, write, and then get my pen, because that makes no sense. Same with the FD cycle. I have to fetch the instruction first. Once it's fetched into the CIR, I can decode it, and once I've decoded it, I can execute it. So every single instruction must go through that process. The output of one becomes the input to the next. So once I've fetched, the output of the fetch is the instruction has been fetched into the CIR, and then that becomes the input to decoding. Once I've decoded the instruction, okay, I know what instruction it is, I can then execute it. So the output of decoding is the input to executing. Okay, so hopefully that makes sense. Now, why is it useful? Well, it does allow efficiency still, because even though a single instruction can only be fetched, decoded, and executed in series, okay, I can have some parallelism, and this is where the misconception comes in. Okay, when I'm doing it, I am fetching one instruction whilst decoding another. Okay, so I'm working on two separate things. So when we talk about a pipeline, we are talking about two separate instructions in this scenario. Okay, so I'm decoding one instruction whilst I'm fetching the next. Okay, it's not doing it in parallel per se, so one instruction is not running in parallel. We can't do all three stages at once, but I can fetch one instruction while decoding another one. Okay, I'm making a big thing about that one because when we talk about normal pipelining, that may not be possible. Okay, it's not always the case that I can do two parts of the pipeline on two different things. So sometimes I might not need to. For example, if you're talking about an instruction pipeline where I have a big long instruction and the output of one part of the instruction, it becomes the input of the next. Well, I have to run each one of those in order, don't I? Okay, and none of them can be run in parallel because I have to wait, the last one has to wait to the one before it finishes, before it can start executing. So it can't run in parallel. So pipeline is a sequence. Okay, so bearing that in mind, there may be an opportunity for parallelism, but there may not be. Okay, that is the big misconception. Hopefully that made sense. Okay, anywho's, in CPU pipeline, there is an opportunity for parallelism. Okay, because we can fetch and decode in different instructions. Okay, so it maximizes the utilization of memory and the cache, but doesn't improve one instruction. Now, this was very similar to the one of the questions you had in the mock, where let's say I've got 5 instructions. Okay, cool beans. Okay, now in the first cycle, okay, what we're doing is we're fetching that instruction. Well, there's nothing else we can do. I have to fetch that instruction in. That then comes in. The next cycle, okay, well, I can decode that first instruction because I've already fetched it in. But then instruction 2 can start to be fetched. Okay, then in cycle 3, well, I can execute that first instruction whilst I'm decoding the second one and I'm fetching the third one, sorry. Now instruction 1 is finished, so I can now execute instruction 2 whilst I'm decoding instruction 3 and I'm fetching instruction 4. Then instruction 3 can be executed and instruction 4 can be decoded an instruction file can be fetched, and we'll just go down that way. Okay, so as you can see, at any given time, when I am fetching, decoding, and executing, okay, let's just take that one example. I'm working on 1, 2, 3 different instructions at once. Okay, so the parallelism is I'm doing all 3 stages at the same time, but on different instructions. A single instruction still is sequential. Okay, if you see instruction 1, I'm still doing it in a sequence. Okay, however, by time I get to cycle 4, I can start to do 3 things at once, or should I say cycle 3. Okay, hopefully that makes sense. Now, just so you're super crystal clear about this one, okay, CPU pipeline is just one example of a pipeline. Pipelines come in many different shapes, sizes, and forms. Okay, so here I've got an example of a pipeline. Now it's a bit of a weird pipeline because I've got action A. Okay, cool beans. That's action A. So that's the first thing that happens in my pipeline. Okay, now the output of that becomes the input to 2 separate things. Okay, B and C. Now these 2 can happen in parallel, okay, because they don't need to wait for anything else to happen. D can't happen in parallel because it has to wait for B and C to both finish. Okay, once B and C are both finished, then D gets the output of those 2 guys, and then it can start to run, and then finally the output of D becomes the input to E. Okay, so what we really have is this idea that we have the output of one activity becomes the input to the next one. That's pipelining. Okay, but sometimes I have the opportunity to do 2 things at once. Okay, not always, but sometimes I do. Okay, the skill for you guys is to understand which one is which. Okay, the exam scenario should be really clear about it. Okay, but please don't just make the assumption that pipelining is always parallel. Okay, it is a key advantage of it, okay, because I can do the pipeline of different instructions, for example, in parallel, but on its own right, on a single item, I get no benefit from the pipeline. It just means that the output one is the input of the next. Okay, so notice that I've highlighted that massively because that's super important. Okay, so what I'd like to do now is have a go at the exam questions.